Good morning, students. So today we are going to discuss the topic coordination compounds. So what are coordination compounds? Yes, what are coordination compounds? So coordination compounds are the chemical compounds, okay, so which consist of a central atom, okay, central metal atom, which are surrounding by a anions called as ligands. Okay, so they make up a chemical compounds which are called as coordination compound. So these ligands are held, they attach the metal to a coordinate bond. Okay, so such type of chemical compounds are called as coordination compounds. So we'll be discussing, so what is addition compounds? Okay, so what are addition compounds? So addition compounds, they are the compounds which are made up of two or more stable compounds by crystallization in a fixed stoichiometric ratio. Okay, so they are called as addition compounds. So these addition compounds are further divided into two. For is complex compound, another is double salts. What do you mean by complex compounds? Complex compounds are in which there is a central metal atom. Okay, there is a central metal atom which is surrounded by non-metals atoms or groups of atoms called as ligands. So in complex compound, there is a central atom which are surrounded by non-metal atoms or groups of atom called as the ligands. Okay, and these are held by chemical bonds. Now, what are double salt? Double salt means what? Double salt. There is a combination of two salts. So combination of two salts are called as double salt. Complex compounds are further divided into types of ligand and charge on the complex. Charge on the complex is further divided into cationic, neutral, and anionic. Okay, so these are so next we'll see different types of complexes. So first is homoleptic. What do you mean by homoleptic? Complexes in which metals is attached to only one kind of donor groups are called as homoleptic. Okay, so you can see CO, right? CO, that is cobalt. So cobalt is surrounded by NH3. NH3 is what? Ammonia. So these are attached to only one kind of donor groups. Then it is called as what? They are called as homoleptic. So all the donor atoms or the ligands are one. It is only one kind. So it is a homoleptic. Next is heteroleptic. Okay, heteroleptic means what? Complex in which metal is attached to more than one kind of donor group. So you can see the example here. Okay, so cobalt is in center. Okay, that is a central metal atom, and these NH3Cl, okay, which are attached, these are the ligands. So here two types of ligands are present. Okay, there are two types of ligand. That is ammonia and chloride ion. So when complexes in which the central metal atom is attached to more than one type of donor, then it is called as heteroleptic. Next is cationic complexes. Okay, cationic complexes, the complex in which the complex ion carries a net positive charge are called as cationic complexes. So we can see this is example. Cobalt is bound by NH3 molecules. Okay, this is NH3 itself, not NH2. So NH3 molecules, and you can see the overall charge. What is the overall charge? It is 3+. So there is a positive charge on the complex. So then it is called as cationic complexes. So when the complex carries a positive charge, and it is called as cationic complexes. Then what do you mean by anionic complexes? The complex in which the complex ion, okay, the complex in which the complex ion carries a net negative charge are called as the anionic complexes. So you can see here Fe, okay, central atom is iron. Okay, so iron is surrounded by what? There are two types of ligand, that is chloride ion and bromide ion. So the overall charge on this complex is what? It is -4. It is -4. So the complex, it carries a negative charge called as the anionic complexes. Neutral complexes. What do you mean by neutral complexes? The complex which do not have any net charge are called as the complex neutral complexes. So you can see this is a compound, okay, a complex compound, so which does not have any charge, so it is called as the neutral complexes. It is nickel tetracarbonyl. Okay, nickel tetracarbonyl. Next is ambident ligand. Okay, what do you mean by ambidented ligand? So a ligand which contains two donor atoms. Okay, a ligand which contains two donor atoms, but only one of them forms a coordinate bond at a time with central atom, metal atom is called as the ambidented ligand. So you can see the example as NH2. Okay, NO2, NO2 minus. So here you can see NO2 minus, it can link either by nitrogen or it can link by oxygen. But at one time, only one atom can get attached to the central metal atom. So you can see the example A and B. Okay, so in this complex, the nitrogen has been attached. Right, in this complex, what happened? Nitrogen is being attached to the central metal atom. And in this complex, what is attached? It is the oxygen. Oxygen of the NO2 minus is attached to the central metal atom. So a ligand, it consists of what? So this is a ligand. NO2 minus is a ligand. So it consists of two donor atoms, but only one of them will coordinate at one time with the central metal atom. So then it is called as what? It is called as ambidented ligand. So we'll go for the next one. So what do you mean by chelation? Okay, what do you mean by chelation? So chelating is nothing but when you have a bidentate or a polydentate ligand. Okay, what do you mean by bidentate, monodentate? So there are a different type of ligands. So monodentate, bidentate, polydentate. What do you mean by monodentate? There is only one of the atom. Okay, one of the atom will get attached to the central atom. Now, what do you mean by bidentate? Bidentate, for example, ethylene diamide. Okay, so so in that two atoms, okay, two atoms can get attached to the your central atom. Polydentate means what? More than two. So there are two, more than two this, okay, metal linking this, then it is called as what? It is called as polydentate ligands. Okay, it can bind to the central atom. So you can see chelation. So whenever you have two donor atoms, so you can see in this particular example, there are two donor atoms. So two donor atoms, NH2 and COO. So here it can, so there are two donor atoms and both are attached to the central metal atom, that is M metal. Okay, and it binds to a single metal. So when two donor atoms, when it binds to a single metal, okay, then a ring-like structure is formed, then it is called as chelation. Chelation is nothing but it forms a ring-like structures, big ring-like structures, then it is called as chelation. Where chelation is found? When you have bidentate or tridentate or polydentate ligand. Okay, so more than two, whenever there are more than two donor atoms in a particular ligand, then it leads to chelation. Chelation is nothing but they form a stable ring-like structure. 5-membered or 6-membered ring they form. Okay, so thus it results into chelation. So we'll solve some questions now. K4, okay, FeCN6 is so what type of example is this? Is it a double salt? Is it a normal salt or a complex salt? Yes. Yes, it is a, yes, it is a complex compound. Okay, it is a complex compound. How you say it is a complex compound? How you say it is a complex compound? So FeCN twice plus 4 KCN. Okay, giving you K4 FeCN. Okay, so this is the answer. So it is a complex compound. So complex compound. Among the following, the ambidentate ligand is. Yes, what do you mean by ambidentate ligand now? What do you mean by ambidentate ligand? Yes, ambidentate ligand means what? Yes, it is NO2 minus. Yes, NO2 minus. Ambidentate ligand means what? It has two donor atoms, right? It has two donor atoms, but only one atom will donate electron to the central atom at one time. So So here NO2 minus either N or O will get attached to the central atom, right? So this is a example. Next. So what is coordination number? Okay, next is what is coordination number? So coordination number or ligancy is the total number of ligands which is attached to the central metal atom through a coordinate bonds or sigma bonds in the coordination sphere. Okay, what do you mean by coordination number? It is a number, total number of ligands. Okay, it is a total number of ligands which is attached to the central bond. Okay, central atom, metal atom through a coordinate bond. So it represents a number of ligands. Okay, it is represents a number of ligands which is attached to the central metal atom. So this is your coordination number. Oxidation state of the central metal ion is the charge. What do you mean by oxidation state? Okay, how do you calculate the oxidation state of the central metal ion? It is nothing but it is a charge which is the central metal atom appears to have when all the ligands are removed along with the electron pairs that are shared with the central atom. Okay, so oxidation state of the central metal is nothing but it is a charge. It is a charge which appears on the central atom. Okay, when you have all the ligands and you remove, so that whenever the ligands are removed, so they take its pair, shared pair of electrons along with it. Okay, so this is the oxidation state of central atom. So next, coordination number and oxidation state of the element E in the complex R. So now we are going to coordination number of oxidation state of the element E in the complex E and C2H4 NO2. So we have to find the coordination number and oxidation state of E. Yes, what is the coordination number? What is E? Yes, what is E? En is what? En is your ethylene diamond. Okay, it is a bidentate ligand, bidentate neutral ligand. So it is 0. Okay, the charge is 0. Then C2H4. Okay, C2H4 is a bidentate ligand which is carrying a negative charge. Okay, so coordination number will be 6. Okay, the coordination number is 6 and oxidation number is 3. Yes, the answer is A. Okay, the answer is A. So next in the complex is FeCN6 3 minus. Okay, in the complex is FeCN6 3 minus and CrC2O4 thrice 3 minus. The respective coordination numbers of iron and chromium are. So you have to find the coordination number of iron and chromium. Okay, how do you calculate? What is Cn? Cn is a monodentate ligand. Okay, so it has a -1 charge. So X plus 6 into -1 equals to -3. Okay, X is equals to X minus 6 equals to minus. Okay, so what it will be? Solve and see. Yes. Yes, the answer comes to B. Okay, the answer is B. Okay. Yes. So we'll go for the next one. In the complex ion CO NH3 6 times plus 3. Okay, hexamino cobalt plus 3. The ammonia molecules are linked to the central metal ion by dash bonds. So which are the bonds where your ammonia? Okay, so this is your cobalt and this is ammonia. How many ammonia are there? Yes, which is the bond? Yes. Okay. How it is linked? This is your coordinate bond. Okay. It is C. The answer is C. So this is a structure. So how you represent like this? Okay. 3 plus. Understood? So we'll go for the next one. So in aqueous solution, the complex compound do not furnish all the simple ions, but instead give more complex ions. Okay. For example, potassium argentocyanide does not form Ag plus and Cn minus simpler ions, but instead they give argentocyanide complex ion, which does not dissociate along with the K plus ion. So example, K4FeCN6 gives you 4K plus FeCN6 4 minus. Hence, this complex produces totally 5 ions, that is 4 simple ions and 1 complex ion. Okay. So whenever you have an aqueous solution, they do not completely dissociate. Okay. They should after dissociating, it should give us simpler ions, but hence they produce some complex ions. So here there are 5 ions which are produced. So 4 plus K plus ions and 1 complex ion is produced. So that is 4 simple ions and 1 complex ions. Okay, whenever you have aqueous solutions. So the number of moles of ions given on complete ionization of 1 mole of hexamino cobalt chloride is. Yes, how much ions it will give? So if CO, NH3, Cl3, okay, it dissociates to give you what? Yes. So CONH3, 6Cl3, and it ionizes to give you ONH3, 6 times 3 plus 3 Cl minus. Okay. So hence it produces 1 complex ion and 3 simple ions. So totally the total number of ions is what? It will be 4. The answer is B. Okay. The answer is B. I hope you are understanding. Okay. So on ionization of 1 mole of these complex, it will give you 4 ions. Okay. So next we'll see, so which are the negative monodentate ligands. Okay, so we'll be writing the IUPAC name. So first we'll see, so you will be knowing the IUPAC nomenclature, how to write. So we'll see which are the different monodentate negative ligands. So this is Cn minus, okay, it is cyanide ion. So name given in the complex. So whenever you're writing the name in the complex, it is called as cyano. Halide ions like F minus, Cl minus, Br minus, I minus, the name is fluorido, chlorido, bromido, iodido. Okay, iodido. Then hydride ion, that is H minus. When you are writing the, when you are, okay, you are giving the name, it is called as hydrido. It is hydrido. Then nitro, that is NO2 minus, this given name given in the complex is nitro. Nitrite ion ONO minus, it is nitrito. Okay. Then nitrate ion NO3 minus, NO3 minus, then it is nitrato. Then this what? Hydroxide ion, that is OH minus, it is hydraxo. Amino, it is amido. Okay. So these are the monodentate negative ligands. Then amide ion, if you have NH2 minus, it is amido. Imide ion, that is NH2 minus. Okay, raised to it is imido. Nitride ion, N3 minus, nitrido. Azide ion, that is N3 minus, azido. So the names Cl minus, Br minus, I minus, F minus, Cn minus are still used. That is chloro, bromo, iodo, fluoro, cyano are still used. So some of the polydentate ligands, okay, polydentate ligands of oxalate ion, okay, it is the formula is CO minus, COO minus. So the name given is oxalato. Acetyl acetonate, okay. So this is the compound, this is the formula, it is acetyl acetanato, okay. Then this is glycine, okay, glycine, acetic acid, it is a glycine is amino acetic acid. So it is glycinato, okay. Then pentadentate. So these are the examples of pentadentate. These are didentate. Okay, didentate. Why? Because they are linked by two. So okay, they are linked by two sources, two atoms. Next is pentadentate. Okay, pentadentate. So you can see ethylene diamine triacetote ion. That is EDTA. These are called as pentadentate. Okay. So ethylene diamine triacetato. Then hexadentate is ethylene diamine tetraacetate ion. Okay, EDTA 4 minus. So this is ethylene diamine tetraacetato. So these are the names. So now when you are writing the name, okay, now this is the cationic part. So cationic part Na2 2 plus, and ZnCl minus is your anionic part because it is having the overall charge 2 minus. So first outside the complex, you have to write that, okay, whichever the metal is present, sodium. Then according to your ligands, okay, the with your alphabetical order, now it is Cl come first. So you have to write how many chloride atoms are there? There are 4. So it is tetrachloro. Then your metals will always end up with 8. Okay, so it is zincate. So how do you find the overall charge? So find the overall charge. You can find the oxidation number. So it is x plus 4 minus gives you minus 2. Okay, so then x is equals to minus 2 plus 4. So the overall this will be minus 2. So the zinc, the oxidation state is 2. So like this, you're going to find one more. So this is a negative part. This is a negative complex because overall charge is minus 3. So how the name is given? So first you have to name your ligand. So it is trioxalato. Okay, trioxalato, cobaltate. Okay, cobaltate. Then the cobalt is having the charge 3, and then you have to write ion. Okay, so you have to find the after writing the charges of oxalato and this minus, so you have to find the your charge of the cobalt. Okay, so these are the ways. One more example. So you have an anionic part this side, okay, and you have a cationic part here, because overall charge on this complex is what? It is plus 2. So this is a cationic part and this is an anionic part. So first aqua comes or your amine comes, right? Because AQ, before AQ, AM comes. So how many moles of amino are there? There are 5 moles. So it is pentaamine. Okay, then diaqua, then copper 2, and then your chloride. So you have to find out the right. So your water molecule is having 0 oxidation state, amino is having 0. So the overall charge will be plus 2. So like this, you're going to write the names. So based on this, so we'll start writing the IUPAC name for the complexes. Okay. So IUPAC name of PT. Okay, this is PT in bracket NH3 thrice Br NO twice Cl. Overall bracket close. Then Cl is, what is the name? Yes. What is the IUPAC name? Follow the rules. Follow the rules and name the complex compound. Yes. Name the complex compound. Yes. So between your amino, so which are the ligands? Amino, Br, okay, that is bromido, then chlorido and nitro. So which comes first? Amine comes first, right? So to follow the alphabetical order. How many amines are there? Tri. So triamine, right? Then after amine, which comes according to alphabet, bromine. So it is bromido. Then comes your chlorido. Then comes your nitro. Then platinum. You have to find the charge. Platinum, the charge comes to 4 and it is chloride. Okay, so the answer is C. Okay, the answer is C. Yes. So we'll go for the next one. I hope you're understanding. So you have to follow the alphabetical order. IUPAC name of IUPAC name Na3 in bracket COONO bracket close 6 times. Okay, what is the name of this complex compound? See, whenever you have metal outside the complex, first you have to take the name of the that metal first. Okay, then you have to follow the alphabetical order to naming the your ligands. So what is the name? Yes, Rakshita, it is D. Sodium hexanitrito cobaltate 3. Okay, sodium hexanitrito cobaltate 3. Okay, so this is the answer. Yes. So we'll go for the next one. Which among the following will be named as dibromido bis ethylene diamine chromium 3 bromide? Yes. Which among the following will be named as dibromido bis ethylene diamine chromium 3 bromide? So before this examples we have seen, they have given a complex and they told us to name it. Now they have given the name. So accordingly, we have to write the complex now. Dibromido means what? It will be Br2. Okay. Bis ethylene diamine means what? It will be ethylene, which is represented here like this. Cobalt 3. Okay. Cobalt 3 and so it will be like this and then your Br. Okay. So what will be the answer? It will be B. The answer is B. Okay. The answer is B. Right? Dibromido means 2Br. Bis ethylene diamine means ethylene is represented as En. So twice, then you write your chromium 3. If chromium 3 is written, the bracket is closed and your bromide comes outside, right? So it is like this. So the answer is B. Okay, so we'll go for the next one. So valence bond theory. Okay, so metal and ligand is there. So ligands, what? So here the metal, they always tend to likely to accept the electrons. Okay, so they are called as electron pair acceptor. So these metals, central metal atom, they act as a Lewis acid. Okay, they act as a Lewis acid. So they have vacant orbitals. That is, they have s, p, and d vacant orbitals in the metals. Then ligands. So ligands are always in the ease of giving the electron. Okay, so they always donate the electron pair. So always the ligand, they will tend to give the electrons to the metal because metal is a good acceptor, electron pair acceptor, while ligand is a electron pair donor. Okay, so this, so if, as it is donating the electron pair, then it is called as what? It is called as Lewis base. So here, as you can see in metal, they have empty d orbitals. Okay, they have empty sp and d orbitals. In your ligands, they have filled orbitals. Okay, they have filled orbitals. So we'll see the postulates of VBT. Central metal ion provides a definite number of vacant orbitals, that is sp and d, for the formation of coordinate bonds with the ligands. So the first postulates of VBT, that is valence bond theory. So as we have discussed, that the central atom, it will provide a definite number of vacant orbitals, that is sp and d, for the formation of coordination bonds with the ligand. Next is what? Each ligand has at least one orbital containing a lone pair of electrons. Why? At least one orbital it has, which has a lone pair of electron, because it is acting as a Lewis base. So it has a tendency to give the electrons. Okay. The number of vacant orbitals provided by the central ion is the same as its coordination number. So this is the third VBT. So you can see this is the first one here. This is your metal, metal with all the orbitals empty. Okay, and this is your ligand which have at least one pair of lone pair of electrons are present. Okay. So you can see these are all empty orbitals in case of your metals. Okay, this is your metal and this is your ligand. Filled orbitals are present in your ligand. Okay. So when they merge, okay, so ligand, what it will do, it will form a coordinate bond with the metal. Okay, so it will give its pair of electrons. So like this, it forms the coordinate bonds. Okay. So the vacant orbital of the metal, what it will do, it will overlap with the filled orbitals of the ligand to form a coordinate bond between the metal and the ligand. Okay, as we have discussed, as the metal, they don't have any orbital, they have a free, vacant orbital. Okay, so what does ligand do? As at least one of the orbitals will be filled. So ligand, what they will do, they will overlap with the vacant orbital of this metal, will overlap with the filled orbitals of the ligand, and they will form what? They'll form a coordinate bond between a metal and the ligand. Okay, so next point. So these coordinate bond. Okay, so this coordinate bond which is formed, it is stronger if the overlap is between the orbitals is greater. If the overlapping between the orbitals is greater, then the coordinate bond formed will be stronger. This vacant orbitals undergoes hybridization to form a same number of hybrid orbitals. Okay, hybridization will decide the geometry of the coordination compound. So next we'll see different type of hybridization geometry. Okay, if you have a sp hybridization, the geometry will be linear. Okay, the linear geometry. So the structure will be like this. Okay, central metal atom, pink represents your central metal atom. Then your central metal atom, and white molecules, it represents your ligands. Okay, so if you have a sp hybridization, so if I have a sp2 hybridization, it is having a trigonal planar. It is having a trigonal planar. So the structure will be like this. Okay, pink in the central atom is a pink, and white is your ligands. Okay, so white represents your ligands. Then sp3 hybridization, the geometry will be tetrahedral. The structure is like this. Okay, pink is your central atom and white represents your ligands. If you have sp, so another, if you have sp3 hybridization, it will show square planar. Okay, square planar. Pink, the central atom is a pink. Okay, and white represents your ligands. That is square planar geometry. Okay, this is a square planar geometry. So if you have sp3, it will undergo tetrahedral and square planar geometry. It will show either of this. So this is octahedral. Okay, this is octahedral geometry. This is your, okay, this is your octahedral geometry. This is octahedral geometry. When octahedral geometry is, you get octahedral geometry when you have D2sp3. Okay, when you have D2sp3 or you have sp3 D2. Okay, so these are the different hybridization and geometry. So whenever you have D2sp3, then they form inner orbital complex. Okay. And when you have sp3d2, then they form outer orbital complex. So we'll see some of the structures. So structure of tetra carbonyl nickel nickelate is this. Okay. So this is a structure of tetra carbonyl nickelate. Okay. So this is a tetrahedral structure. So it is a tetrahedral structure. So structure of NiCl4 2 minus. So this is a structure of NiCl4 2 minus. So it is a tetrahedral structure. So you can see the structural representation. So structure of NiCN4 2 minus. Okay. So it is a square planar. So this is a square planar structure. Then structure of COF6 3 minus. What is the structure of COF6 3 is COF6 3 minus? So it is a octahedral. So you can see octahedral cobalt in the center. Okay. And okay, so these are the bonds. So this is octahedral geometry. So we'll see some of the questions now. So which complex has a square planar structure? So we have seen some of the structures now. So which complex will have a plane square planar structure? Yes. Which compound will have a square planar? Yes. Which compound? So you can see the structure. It is having a square planar. Okay. So NiCN4 2 minus. Right. So NiCN4 2 minus. The answer is what? The answer is C. The answer is C. Okay. Answer is C. So in NiCN4, so in NiCN4, okay, NiCN4 2 minus, the strong fin ligand cyanide ion is there. Okay, so so what it does, it makes forcibly pairing of electrons in d orbitals of nickel. So hence one of the d orbitals will be available for hybridization. So due to which dsp2 hybridization takes place, and thus it will have a square planar geometry. Okay, so this is the structure. So the structure, correct structure for FeCO5 is, that is pentacarbonyl. Okay. What is the correct structure? For FeCO5 is. What is the structure? Yes, it is a trigonal bipyramidal. Okay, so it is a trigonal bipyramidal. So the answer is what? It is A. So the answer is A. Okay, trigonal bipyramidal. So we'll go for the next one. Yes. So which one of the following is an outer orbital complex and exhibit paramagnetic behavior? Yes. Which one of the following is an outer orbital complex and exhibit paramagnetic behavior? Yes, the answer is D. Yes, the answer is D. That is CONH3, that is hexamino cobalt 3. Okay, ion. So here, if you consider A, so your nickel, okay, nickel is in +2 state, thus it becomes 3D8 4s not. Okay, so this is the electronic configuration. So to accommodate the 6 ligands, okay, of ammonia, then two orbitals, 2d orbitals should be empty there. Okay, but here 2 3d orbitals are not vacant here. So here 2 3d orbitals are not vacant. So this is wrong. So this is not available. It will not form an outer orbital complex and a paramagnetic behavior. Next, if we consider B option, that is zinc. So zinc will have Zn +2. The electronic configuration will be AR 3D10. Okay, so here the complex found will be outer orbital complex, but the paramagnetic behavior, it will be a diamagnetic behavior. It will show diamagnetic characteristic. So this is also overruled. Then if we consider C, okay, if we consider C, your chromium is in +3 state, the electronic configuration will be AR, argon 3D3. Okay, 3D3. So argon 3D3, argon 3D3. So this will form inner orbital complex. Okay, it will form inner orbital complex and it will show a paramagnetic behavior. So this is also overruled. C, that is compound here. So the electronic configuration is argon 3D6. Okay, so 6 electrons are there in 3D orbitals are paired to leave 3D orbitals vacant to occupy the two ligands, and hence the complex formed will be your okay, outer orbital complex. So here they make use of the outer 4D orbitals. Okay, so outer 4D orbitals are there. So hence what it will do, 4D orbitals are involved, thus it forms outer orbital complex and it will be showing a diamagnetic behavior. Okay, paramagnetic behavior. So this is the answer. The answer is D. Next, we'll see crystal field theory. So in crystal field theory, you have a metal and your ligand. So metal. So ligand, as we have discussed, it will be what? It will be acting as a Lewis base. Okay. And so neutral with lone pair of electrons. So ligand will be neutral with lone pair of electrons. They will be negatively charged. So if they are negatively charged, so these, okay, then metal. So metal, they are Lewis acid. So they act as a Lewis acid. So metal, it will, what it will do, it will form, so the force of attraction between the ligand and the metal, there is a electrostatic force of attraction. Okay, so they act as a point charges, ligand act as a point charges when you have a negatively charged molecule. So these are the orbitals. There are 5d orbitals are present. Okay, there are 5d orbitals which are present in your d orbitals. So these are said to be having same energy. When you are saying it as same energy, when they are called as degenerate, the word is degenerate. Degenerate means all the orbitals in the d orbital, it is okay, all are having the same energy, that is they are degenerate. So they will, so in the influence of the ligand, okay, when they come in influence of the ligand, they will form, okay, they will go to our upper. So when a ligand comes in contact with the metal, okay, so they will form, just here, it does not takes into account any overlapping and rules out the possibility of covalent character. Okay, so when the approach is there, so we'll see tetrahedral complexes and octahedral complexes. So dx, dyz, dxz, dx square minus y square, and dz square. So these are the orbitals. Okay. So these are the different orbitals, how they are represented: dxy, dyz, dxz, dx square minus y square, and dz square. Okay, so this is a representation. So it will form what? These are the octahedral. Okay, these are the octahedral complexes. So this way it is represented. So whenever it is along the axis, okay. So whenever the ligand is along the axis, so it will that is dxy, dyz, and dxz. They are along the axis. Okay, they are perpendicular to the plane. Okay, of the metal, and so you can see, okay, dx square minus y square. Okay, they are along the plane. So when they come in contact with the ligand, okay, they will split into, okay, dx square, dy square, dz square, So in between the axis, so they are in between the axis. So as they are in between the axis, they will and these dz square dx x square minus y square, they are on the axis. Okay, they are on the axis. So what will happen? So they will split. So dx, this is dxy, dyz, and dxz. Okay, and this is a dx square minus y square dz square. So the crystal field splitting takes place. Okay, in the presence of ligand, the d orbitals, they separate, or they split into this. Okay, this T2G and EG. It represents the T2G and EG. So this results into complex field splitting. Okay. So this is EG. The upper one is called as EG, and downward is called as T2G. So the barycenter, okay, it is 0.6 delta O. This upper represents 0.6 delta O, and lower is 0.4 delta O. Okay, so this is plus, this is minus. So this is your barycenter. So complete barycenter is delta O. So complete barycenter is 10 dq. Okay, it is given as 10 dq. So 0.6 delta O is nothing but your 6 dq. So these are the calculation parts. So whenever you have a strong field ligand and a weak field ligand, what happens? Okay, in between the presence of strong field ligand and weak ligand. So it's split into EG and T2G. Okay, so this is a barycenter, EG, and T2G. Whenever you have a strong field center, it will have a more crystal field energy. The barycenter will be more. Whenever you have a weak field ligand, the barycenter will be small. Okay, so you can see the delta naught. Okay, that is delta octahedral. The value will be more in case of your strong field ligand, and in case of weak field ligand, it will be small. So more splitting will take place in strong field ligand, and less splitting will take place in weak field ligand. So here the delta O is more, here the delta O is less. Okay. So crystal fields splitting in tetrahedral complex, we'll see. So what happens here? So this will split into T2G, EG. Okay, so up your dx square. So this is a splitting. You have already studied this. So I'll just go faster. So it splits into T2G and EG. Okay, so the barycenter here is given as 10 dq. So upper will be 0.4, down will be 6 dq. Okay. So this is the crystal field splitting energy that is given as delta T, because this is in case of tetrahedral complex. Okay. So the splitting of D level in the tetrahedral crystal field is much less as compared to the octahedral field splitting. Okay. Each electron entering into the low energy, that is orbital, stabilizes the EG, will stabilize the complex by 6 dq. Then each electron entering into the high energy T2G orbital will destabilize the complex by 4 dq. Okay. So whenever you have a strong field ligand, remember it will undergo a high splitting power, and whenever you have a low ligand, weak ligands, it will undergo a lower splitting power. Okay, so the common ligands can be arranged in a series in the order of their decreasing strength. So this is given as electrochemical series, spectrochemical series. Okay, so these are the decreasing field strength of the various ligands. Okay, so this series will depend upon the power of splitting in the d orbital. So magnetic property of these two compounds. So Fe, in case of Fe F6 3 minus and Fe Cn6 3 minus, so Fe plus 3. Okay, this is in both the case Fe is plus 3. The electrons present in the d orbitals will be 5. So how the splitting will take place? So it will undergo a high spin complex. Okay, it will undergo a high spin complex, and in case of FeCl6 minus, okay, it will undergo a low spin complex. Okay, so it will show a low spin complex. So now we'll see some of the questions. Which complex of CO plus 2 will have the weakest crystal field splitting? Yes. So see which will have a weakest crystal field splitting. This is spectrochemical series is given down. Okay. So it was in order of their decreasing strengths. Okay, decreasing strength. So which will show a weakest crystal field splitting. Yes, it is B. Okay, it is a B, that is Cl minus. Okay, it is B, that is Cl minus. Yes. So the crystal field stabilizes energy. CFC is highest for A, COF6, B, COCNS4, 2 minus, CONHC6, 3 plus, and COCl4, 2 minus. Yes. The crystal field stabilization energy will be highest for. So if you have a strong field ligand, then the crystal field energy will be more. If you have a low weak field ligand, then the crystal field energy will be less. Right. So what is the energy? It is. You can see this. It is. You can see the spectrochemical series. Yes, you can see the spectrochemical series. You can see here. Yes, according to the spectrochemical series, you can just see crystal field stabilization energy will be more for what? Yes, it is C. Yes, it is C. Yes, it is C. So we'll go for the next one. Isomerism. Okay, what do you mean by isomerism? So it is a phenomena in which compounds have same molecular formula but will have different structures. Okay. Now isomerism is divided into two types: structural isomerism and stereoisomerism. So we'll see structural isomerism. So what is structural isomerism? So in this, first is ionization isomerism. Ionization isomerism is nothing but when the compound will give you different ions in solution, although they have same composition, are called as ionization isomers. Okay. So although they have the same okay, the composition is same, but when they dissolved into the water, okay, or different solutions, what the different ions in solutions, the compound will be giving you different ions. So this is termed as ionization isomerism. Then the next is hydrate isomerism. Hydrate isomerism have the same molecular formula but differ in the number of molecules of H2O inside and outside the coordination spheres. So you can see example here. So based upon the number of water molecules which are differing in each complex, you can see they are showing various color variation. So in the first compound here, you can see the color shown will be violet. Okay, if you have 6 hexamolecule. If your one molecule, water molecule is associated outside the sphere, it is blue-green. And here you can see it is green. So based upon the number of water molecules, it is the variation, it is showing different water molecules. Okay. It is showing different colors. So next we'll see linkage isomerism. Linkage isomerism have the same molecular formula but differ in the linkage of the ligand to central metal atom. For example, what? Ampidentate ligand. Okay, so here ampidentate ligand we have seen. So either one of the, so there are two donor atoms, so either one of the atom will get attached. Okay, so then it is called as ampidentate. So you can see two examples. So if oxygen atom is linked to cobalt, it forms a red color complex. If N, nitrogen is attached to the cobalt, it forms a yellow color complex. So this is called as linkage. It is based upon the linkage of the ligand to the central metal atom. Next is coordination isomerism. The isomerism which is caused by interchange of ligands between the two complex ion. Okay, so it is between the two complex ion. If you interchange then of ligands, then it results into a coordination isomerism. So we'll see some questions. So the complex ions, okay, so these are two complex ions. So these are called as what? They are called as what? They are called as, yes, so these are the two complex ions are given. So based on the examples you can tell me what they are called as. Ionization isomers, coordination isomers, linkage isomers. Yes, they are called as linkage isomers. Okay, so it is linkage isomers. So the answer is B. Yes. So we'll go for the next one. So the which of the following is a pair of coordination isomers? Yes, which of the following is a pair of coordination isomers? Yes, the answer is B. Yes, the answer is B. You're right. Okay. So the compounds, these are the two compounds. These are examples of what? These are the compounds. These are the examples of what? Yes, they are the examples of hydrate isomerism. Yes, hydrate isomerism. Okay, so we'll go for the next one. Which of the following is a pair of ionization isomers? Yes, which of the following is a pair of ionization isomers? A. Yes, A is the answer. Yes, right. A is the answer. So stereoisomers, they are divided into geometrical isomers and optical isomers. Geometrical isomers, there are planar molecules, complexes. So those we are studying about planar molecules. So geometrical isomer depends upon the spatial arrangement of ligands about the central metal atom. So if the atoms are on the same side, then they are called as cis. If the atoms are on the different side, then they are called as trans. Okay. So so you can see coordination number. So coordination number, if it is 4. So if you want to show cis and trans molecules, so it can be only shown if you have square planar complexes and octahedral complexes. It cannot be shown in a tetrahedral molecules. Okay. So these were some of the So based on the number of ligands, okay, based on the number of ligands, so cis and trans you can show. So in tetrahedral you cannot show, in square planar and octahedral you can show. So one last question. So which of the following complex species is not accepted to exhibit optical isomers? So you have to tell which of the complex species is not expected to exhibit optical isomerism. So among this following. Yes, which will be the, what will be the answer? The answer is C. Okay, the answer is C. So which of the following complexes species is not expected to exhibit optical isomerism is C. Okay. So I hope whatever points we have discussed today, you have understood. Okay. So we'll stop for the day and we'll meet in the next class. Thank you. Have a nice day.